Good evening, all. Welcome to week 7 live session for Fundamentals of Convective Heat Transfer course. So, okay, let me share my screen. Yeah, hope my screen is visible. Yeah. So, this week we'll be discussing on hydrodynamically developed and thermally developing flow circular pipe with both uniform wall heat flux and uniform wall temperature conditions, and subsequently we will see what is the heat transfer in a plane fluid flow. Mostly I'll be focusing on solving problems in this week because there is a lot of theory that is going on in the lecture videos and I don't want to repeat that again. So if you have any queries, we can discuss them. Otherwise, we will just focus on solving most of the problems. So since I'm sharing my screen, I am away from the main tab. So if you have any queries, please unmute yourself because I will not be able to see the chat box directly. Okay, we'll get started. So just to give a quick summary of what the problem that we are trying to solve is, we have a circular pipe and then with the uniform wall heat flux from all the sides, and we are saying that it's a hydrodynamically developed flow, so that the parabolic profile is already established. But then delta T is actually much less than R naught, so that the thermal boundary layer has not been fully developed. So under these conditions, what would happen is what we are trying to understand now. So last week when we were discussing the problem, that was the case when even these both the thermal boundary layers have actually merged together, and that's why we call it thermally also fully developed. But of course, when it is thermally fully developed, this doesn't mean del T del X equals to 0, but then both the thermal boundary layers have merged with each other. That's what we mean when we say thermally fully developed. But in this week, we will be covering the scenario where they are not completely mixed with each other. So the general velocity profile after solving the equation will be of this particular form. So you have the terms that are only function of r and terms that are function of x. So as the flow develops, what happens is these terms that you have with respect to x, this particular term, this summation term would eventually go to 0, and the same would apply here, that this term will also be this term will still remain, and this is the term that, if you recollect from what we have discussed a couple of weeks back when we were doing the scaling analysis, when we plotted the temperature distribution as a function of the length of the plate, and then we found that the temperature will actually vary linearly when we have uniform wall heat flux, and this temperature profile will also actually give you the same relation, that if as the length keeps on increasing, then this particular term would actually go to 0 and we will be left with this term. Yeah, we'll be left with the term over here. This is a linear relation, that temperature will vary linearly with respect to x. Of course, there is this radial variation that we have already discussed in the last week for a fully developed flow. So the most important number that will tell us whether this particular term will actually go to 0 or not is the one that is in this exponential term. So lambda n square times whatever is this term. So this term x or naught divided by r by d is the inverse of this, is what we defined as the Gray's number. This, if the inverse of this, if this particular number is very high, then it means that the thermal boundary layer development has to be taken into account. So only when this value is close to 1 or less than 1 is where you can, or say in the order of 1 or 1 to say 10, 5, 6 or something like that, in that particular values of this particular number, we can assume that it is fully developed. Otherwise, we have to assume we have to consider the thermally developing flow and use the corresponding correlation for Nusselt number. So the correlation is given by this equation. Nusselt number is 2 by this particular quantity, as we derived before. For large values of this particular term will actually go to 0, and then you will be left with 48 by 11, which is the one that we obtained previously. So that would be around 4 point something, 4.66 or something for uniform wall heat flux case. And these values have already been evaluated, and the derivation is there in the lecture videos. You can go through the derivation. We will actually take a problem and see how to actually compute this Nusselt number, and from there determine things. What are the types of questions that you'll be expecting when you have uniform wall heat flux? are basically from an engineering point of view, what we are interested in are what is the total heat transfer rate from the pipe, what is the maximum temperature that is there inside the fluid or inside the walls. These are the types of questions that we'll be interested in with these types of flows. So we'll try to answer them. So let's take a simple problem. So I'll expect you to solve this problem. So I'll wait for some time so you can go through it. I'll explain the problem and then you can attempt solving it and then we will discuss. Consider water is flowing through a pipe at 20 degrees Celsius. The diameter of the pipe is 25 mm and length is given as 2 meter. And mass flow rate is specified as 10 gram per second. If the pipe is heated electrically, resulting in a uniform wall heat flux of 0.1 watt per centimeter square, you have to determine the overall heat that is transferred to the wall, what is the mean outlet temperature of water, and you're also asked to see how the wall temperature will vary as a function of length of the pipe. These are the questions that we'll be answering now. Yeah, I hope the question is clear. So how should we go about solving this problem? Yeah, though I have specified the values of kinematic viscosity and thermal conductivity. If those values are not specified, how would you go about finding those values? So if you recall, whatever derivations we have been doing up until now are based on certain assumptions. When you're attempting to solve a problem, always make it a kind of a habit to verify whether those assumptions are being uh, satisfied or not for that particular problem you are attempting to solve. Okay. But for the first one is actually quite straightforward, determining the overall heat transfer. So these are the values that are given to us. We have the diameter, length, mass flow rate, heat flux, kinematic viscosity, thermal conductivity, Prandtl number, and the inlet temperature are specified to us in the problem statement itself. And the overall heat transfer is a straightforward one. All you have to do is multiply the heat flux with the total surface area of the pipe, which is given by pi dl. It's not the cross section area. This is some common mistake that we actually see when students are attempting. So because the heat flux is happening across around the pipe, so if you see the diagram here, so heat flux is circumferentially acting along the pipe, along the length and along the diameter. So the area that you should be considering here is pi d, will give you the perimeter times whatever is the total length available for heat transfer. So that will be pi dl. So that will give you the total heat transfer. So you can quickly compute that. You have all the values here. Once you have the total heat transfer, how do you calculate the outlet temperature? Yeah, so you can directly use energy balance. You can write Q equal to m dot Cp T out minus T in, and from that you can directly compute what is the actual outlet temperature, which is inlet temperature plus Q by m dot Cp. Q is the value that you already obtained from the previous value. M dot Cp are already provided. Cp of water is not given here, but you know the value of Cp. It's, yeah, 4.182 unit. Yeah, 4.182 kilojoule per kg Kelvin or 4186 joule per kg Kelvin. You can substitute that and then you'll be able to find the outlet temperature. And the next important question is the determining the wall temperature as a function of length of the pipe. So this is the temperature expression that is derived in the lecture videos. So using this expression, we are interested in finding out the wall temperature profile. So how will I get the wall temperature profile? So in this expression is this is the entire distribution at any given point of x comma r, you will determine the temperature. Now the question is near the wall, what will be the value of x and r? yeah, x will keep on varying along the length of the wall, and but r will be equal to r naught. So if I substitute r equal to r naught, then I should be getting the whatever expression I will be getting will give me the wall temperature distribution, right? Once you have r equal to r naught, then you have to evaluate the other terms. As a function of x, you have to evaluate these terms continuously. You have to use the values of lambda and c and rn. You can use that from whatever table I have shown you before. You can substitute that values in the summation. There are 7 terms, so you can substitute all the 7 terms. Okay, there is a mistake here. This should be rn of 1. Yeah. So you can substitute the values from the table, and that should give you the value of tw minus pi as a function of x, because you have substituted r equal to r naught. All the terms here would be in terms of r naught will actually go, and the only variable that will be remaining is x. So you'll be getting p as a function of x, and that is one that we are asking you to plot here. So if you actually do the calculation, so it will be once you have, this is the mean temperature that I have shown here. Mean temperature you can obtain by integrating this over the entire r. This is expression I would get for the mean temperature. You can do this as well, but wall temperature you can obtain by this, and then if you make a plot of these two, okay, for some reason the plot is not showing up here. In a minute. So this is a plot I am getting. So if I plotted the wall temperature and the mean temperature, so you can see that initially the difference between them will keep on increasing, and beyond a point, so if you see the mean temperature and the difference between mean and wall temperature here and here, it becomes constant. So if the length of pipe was even higher, so let's say the length of the pipe instead of 2, if it is say 10 meters, what would happen is you have, so you can see if the length of the pipe is close to 10, you can see the linear profile very clearly here. So this is what we obtained even when we were solving the case of fully developed flow, thermally fully developed case. When we have a thermally fully developed case, then in the last week we observed that the temperature, the mean temperature and wall temperature will vary linearly with x, and that is what we are getting even here using the relation from the case solution, right? Are there any questions? Okay. There are some points I would like to draw your attention to here. The first one here is, if you see, we assume when we were deriving this particular whatever equation that we have derived, we have assumed that the properties remain constant throughout the flow, or whatever length of the pipe. So here the length of the pipe is 2 meters. So throughout 2 meter, the property should remain constant. But here, if you see the property values, we are taking at the mean temperature, and the mean temperature is increasing linearly with respect to x. So where so the equation for the Nusselt number, whatever we have derived, is valid only when these properties are constant, or in other words, within this temperature range 20 to 24. This temperature range is very less. So because the temperature range is very less, the properties will not actually vary so much, and this approximation might be good enough. But if instead of water, if this was a different fluid, then what would have happened? Let's say it's an air or something, then the temperature would not actually be 20 to 24. It could actually be even higher for the same amount of heat flux. Then whatever we have derived in the class will not be applicable, and we have to make suitable modifications accordingly, which we are not covering now. But the point that I would like to emphasize here is, once you get the results, make sure that even the results are consistent with whatever assumptions that were taken in the model that you have used to obtain those results. Also, if you see that as length increases, this goes also linearly, which is what we have discussed in last week. So you can quickly come tell me these are the values you're also getting the same values. Yeah, I think the heat flux is the same, but the maximum exit temperature is a little different for me. So from the plot, this is around 32 point something. So maybe this is 32 point. It is 31.946. You can tell me if you're also getting the same answer. Okay. Are there any questions? Okay. If there are no questions, then we'll move on to the next case. The next scenario is one where we have constant wall temperature instead of uniform heat flux. So what would happen here is the in the previous case, if you recollect, when we assumed the thermally fully developed case and the mean temperature would actually vary linearly, but here the wall temperature is constant and the mean temperature will actually grow exponentially and eventually reach the wall temperature at infinite length. If you have infinite length pipe, then it would eventually reach the wall temperature. That was the relation we obtained in the last week. So now if you extend that for the region of thermally developing flow, then the temperature distribution will again be of the same form, where it will have some terms like this, and then the Nusselt number is given by this expression. So this Nusselt number is the average Nusselt number. So average Nusselt number is given by this expression. So you can compute this expression using the values given in this table. So you can quickly substitute, for example, here I have given up to 4. So why are we stopping after 4 is if you try to evaluate these terms, what would happen is the the summation, the terms would actually, as you keep on increasing from 1 to 2, this will be like up to say 2 decimal places, and this will be beyond 3 decimal places and 4 decimal places. It will actually decay very fast. So taking up to 4 terms would actually give you a reasonably accurate solution. So first you calculate theta m for using gn and this particular expression for that particular x, whatever x you have. This is a mean value. There is also an expression for determining the local Nusselt number also, which I will show in a little while. But calculation is straightforward. So all you have to do is take these values, do a summation to get the given x, whatever is it, find the Nusselt number, average Nusselt number, use that average Nusselt number to determine the heat transfer coefficient and multiply that with Tw minus Tm, which should give you the total heat flux. So in a uniform heat flux problem, the calculating the net heat transfer is straightforward. However, the determining the temperature is where there were you have to use is something that is little complicated than finding the heat transfer. But in this problem, where you have uniform wall temperature, calculating the since wall temperature is already given, the maximum temperature inside the fluid that it can reach is the wall temperature, which is already known. So the problem here is to determine what is the net heat transfer rate. So let us take the same problem, I mean similar problem that we have taken in the previous case, something like this. So you consider the scenario of laminar flow in circular duct. Hi, good evening. Yeah, so you can try to solve the problem. So you have a laminar flow to a circular duct where length is given as 200 times the diameter of the pipe. Prandtl number is 100 and Reynolds number is 1000. So first we have to identify whether this is a fully developed or a developing flow. Then determine what is the Nusselt number at the end of the pipe, assuming that it is fully developed and assuming it is thermally developing, and see how much error you would be getting if you make the assumption wrong. Is the question clear? Yeah, I guess the question is clear. So these are the values that are provided in the problem. So how do we check if it is fully developed or not? So we check whether a particular non-dimensional number, the corresponding non-dimensional number, yeah, I should have given it the other way around. One by zz is L by d times RED by PR, and check if that number is very much less than 1. If it is very much less than 1, then it is not fully developed. So if the flow is developing, then we have the inverse of Gray's number to be very much less than 1. Or put in other way, you compute the RED, Reynolds number times Prandtl number into D by L, and then see if that is very much greater than 1, then you can say that it is a developing flow. Either way, whichever way is convenient to you. You can you have all the numbers here, so you can directly substitute them and compute that value. Once you have that number, it appears that it is very much less than 1. So it is in developing design. So if it is in developing design, in order to determine the local Nusselt number, this is the equation that you have. So you have to substitute the values of lambda into this expression, where x, in place of x by r naught, you will substitute this value. So L by D will basically be L by 2 r naught. So L by r naught will be 400. You can substitute that here and then compute the value of local Nusselt number. The values of lambda and Cn are given here. Once you compute that, this is assuming it is a developing flow. Now let's say you didn't actually check the value of this particular number and you assume that it is fully developed. What would be the Nusselt number if it is fully developed? Maybe I'll wait for some time. Compute the value of this local Nusselt number first. Are there any questions in calculating this number? It is straightforward, right? You have to take the values of Gn from this table, multiply that with the exponential of this lambda n squared times, this is basically 1 by this particular value that you have already calculated before. So it will be 2 times whatever you have calculated here, multiplied with lambda n square. The value of lambda n is already given here. You just substitute those values and then take the summation. That should give you the local Nusselt number. And what would be the Nusselt number for fully developed case? So this is constant wall temperature boundary condition. So it will be around 3.66. So if you can if you have the values of this one, just compare that with the other one. So it says that assuming that the average Nusselt number will be approximately twice the local value, what would be the error that you would get? Are you familiar with Python or something? So if you're familiar with Python or any other programming language, you can do this very fast. So all you have to do is plug in the values of lambda n and gn, and then just put the expression over here. That should give you the value of Nusselt number as around 7.7. But under the fully developed conditions, we have it around 3.66. This is the value for fully developed case. So you can compute the error as 1 minus 2 times that given by this. So that is giving me around 321% error. So make sure you calculate this before assuming it as fully developed. Are there any questions? Okay, I guess there are no questions. So we have taken one constant heat flux problem and one constant temperature problem. The next set of lecture videos focus on plane fluid flow, wherein you have two different cases. So basically you have two walls, one of them is moving at a constant velocity, and then the velocity profile between them is assumed to be uniform velocity. Now you can have two different boundary conditions for temperature. Either you can have isothermal walls like this, or you can have one of them to be adiabatic. These are the two cases that are solved in the lecture videos. So the the new non-dimensional number that is coming here is the Eckert number and the Brinkman number. So this Brinkman number is what that is useful for us. So the expressions are already taken from the lecture videos. I hope you've already gone through the lecture videos. So I'm not going through the derivation of them. So if you have any doubts, we can discuss them. So the Nusselt number values are directly given here. So you can use them to determine the heat transfer, etc., whatever is required, asking the problems. We will take up one problem on that. And then you also have adiabatic case. So when you have one of the walls as adiabatic, the questions that we would be asking is what is the heat transfer from the top wall? That is an obvious question. And the next important question is, because this is adiabatic, the heat energy cannot escape from this side. So the temperature here would actually be different from the fluid temperature or the other wall temperature. So if there is viscous heating, that is the case that we are, so that was the main point, important point here. So if the velocity is very high, and then because of the velocity gradient, there will be high viscous heating, and that viscous heating would actually increase the temperature. When the wall temperatures are TH and T0, which means if one of them is actually lower than the maximum temperature inside the fluid will actually be cooled. But when you have one of them to be adiabatic, then there will be heating near the wall. And the next important question here, what would happen? What would be the maximum temperature of this wall? That would be the question that is interesting in this. So there is, so this problem is one of the applications of that. So you have, let's say, a journal bearing. Journal bearing is one that you use when you have a very high speed shafts. So the shaft will be inside the journal bearing. So this is the bearing and this is the shaft. The white one here is the shaft. So this is a bearing, and then we don't want this shaft to touch the bearing. Otherwise there will be a lot of friction and noise and stuff. So what we do is we put some lubricant inside. So what happens is, as the shaft rotates, there will be some hydrodynamic forces which we are not discussing. Our objective is to understand, as this rotates, there will be some small gap between these two elements, and within that gap there will be oil. So you can see the oil flows within that gap. So if the thickness of this particular gap is very small compared to the radius, then we can assume this to be like a straight line. So whatever we have discussed in the class as the plane fluid flow is, this is a classic case of that. So here, let's say the diameter to be 100 mm and the thickness of the oil film to be 0.5. So if you take the ratio of this to diameter, this is very small. So it's like 1 by 200 or something. So because it is very small, you can assume it to be almost like a plane fluid flow. You can assume the velocity, the shaft will be rotating. So the top plate is having with the velocity u, which is given by the shaft is rotating with the given omega, and you know the diameter. So you can calculate what is the velocity at that point, at the tip. The tangential velocity will be the velocity that is given into the in the previous problem. So in the here, whatever this u here we are saying is basically now r times omega. And if the shaft is maintained at 80 degrees Celsius and bearing is well insulated, which is usually the case, the most important question now is, what would be the maximum temperature in the oil film? Yeah, I guess the problem is clear. Maybe I'll wait for some time. You can quickly solve it. This would be very important because, let's say, if you are if because of this viscous heating, because of this high speed, because the shaft is rotating at a very high speed, the velocity and the Brinkman number will be very high, and you have to accordingly select the oil, because one of the main assumptions that we have considered here is that properties do not change throughout whatever flow that we are considering. We have assumed properties to be constant. If, for example, the oil undergoes some chemical decomposition at some high temperature or something, then you have to carefully select what material you are using. So it is important to understand what is the maximum possible temperature that can happen inside these circumstances, and then accordingly design what oil you want. So how would you go about solving this? These are the values that are given to us. We are assuming that the flow to be plane fluid, and you can determine the velocity as pi dn by 60. First thing we have to check is whether our assumptions are valid. The first assumption is we are assuming it to be laminar. So compute the Reynolds number and see if the laminar assumption is valid or not, which is true in this case. And the maximum temperature is given by this expression that I have shown this before in the before slide. So Tmax is given by Th plus mu square by 2k. You know all the values, you can substitute that and get the value of Tmax. So I'm getting Tmax to be around 174.9 Celsius, which is actually quite high because the shaft is maintained at 80 and this is maintained at 174. So the difference of around another 84 degrees, 94 degrees Celsius. And all this 94 degrees Celsius is getting because of viscosity. So because of this frictional forces, this amount of heat is getting generated, and that is actually increasing the temperature of the bearing. Yeah. Are there any questions? Okay. Let's quickly solve another problem. So let's say you have a flow with a constant property fluid and with a given mass flow rate m dot in an electrically heated tube of diameter d and length L. However, unlike the previous problems that we have discussed, the heat flux to the fluid along the plate is now varying sinusoidally. So it is not constant. It is not linearly varying, but it is varying sinusoidally. So maybe you have some coil or something in such a way that it varies sinusoidally. Now assume if q double prime, q naught prime is constant. So this is the amplitude is constant, but then along x direction it is varying. Well, how would the tube surface temperature vary along the length? Assume the heat transfer coefficient to be constant and the value is known. First thing is you understand what is happening here. So take a small control volume here. So this is what we have done when we were deriving even before also. For this small control volume that we are considering, if you write the energy balance, so m dot Cp times dTm should give you whatever is the heat flux that is added, that is whatever Q into whatever this Px that you have considered. So m dot Cp dTm across the control volume is H times Tw minus Tm. Okay, so times dx. That should be equal to Qw prime times dx. You can integrate this equation, determine Tm, and once you have Tm, I can compute Tw from this equation, right? So first take this term and this term. You integrate that equation. You know what Qw prime is. If you integrate that, so I'm getting Tmx by better than that. So if you integrate that equation, so I'm getting Tm of x to be whatever is the inlet temperature at x equal to 0, whatever is the mean inlet temperature, plus the term over here. So because it is sine, if you integrate between 0 to whatever that particular length is, you have 1 minus this particular term that will be coming. And the next question is, once I have this, I can use this the other part of the equation and solve for Tw of x. So basically Qw prime is h times Tw minus Tm, and I know the value of Tm, and this equals to this, so I can calculate Tw to be Tm plus this entire term divided by the heat transfer coefficient. And we are able to do this because in the question it is assumed that the heat transfer coefficient is constant and it is known and given to us. If we do not know the heat transfer coefficient, or if we are unsure whether it is constant, then we cannot do whatever we are doing here. If you substitute, then you will directly get the expression for wall temperature. Okay, are there any questions? If there are no questions, then we'll move on to the next problem. This is also a straightforward one. Consider the laminar flow of oil inside a duct with Reynolds number of 1000. The length is 2.5 meter and diameter is 2 centimeter. The duct is heated electrically by use of its wall as an electrical resistance. Because it is electrically heated with some heater, you can assume it to be constant heat flux. The properties of oil at average oil temperature are directly given to you, so you don't have to do the calculate different temperatures, calculate meters, all of that. All the values, the property values are given to you directly. Obtain the local Nusselt number at the end of the duct. So this question is again straightforward. First you have to check whether it is fully developed or not. And then if it is fully developed, use the Nusselt number for fully developed case, and if it is not, use the one from the developing flow condition by substituting x equal to that particular length of the pipe, length of the duct, which is 2.5 meters. Yeah, I will wait for some time. Have you determined it? You have to calculate the case number. That is very much greater than 1. So I can assume that it is to be thermally developing flow, right? So as I said before, because it is heated by a heater, you can assume it to be constant heat flux. So we'll use the correlation for constant heat flux, and all these values can be taken from the table that I have already given before. I'm getting this around 14.286. And if you compare this with the case for a constant heat flux, which is around 4.36, you can see how much the difference is between this local Nusselt number and the one you have used for fully developed case. So if you have used it incorrectly, then it is around more than 3 times higher. So it would be like 400 to 500% error that you will be getting if you use the wrong correlation. So all of this is to again emphasize things. So the gate or the checking criteria is your Gray's number, which you compute and see whether that value is very much greater than 1 or not. Ideally, 1 is not a correct value, even if it is sometimes close to say 5 or something, then 1 by z will be around 0.2, and even in that case, your Nusselt number will actually be very close to 4.36. This need not be exactly 1, it can be a little higher. So maybe you can consider 10 sometimes, depending on what is the level of accuracy that you're having. And it also depends on what are the how much certain you are about the Reynolds number and Prandtl number that you have input into this particular value. If you're very uncertain about these values itself, then there is no point in all of this. And you have to be more conservative and consider values very much greater than 1. So let's say very much greater than 0.1 or something. But if you are very sure about these values, then you can make this a little higher, up to say 10 or something. It depends on the particular use case that you are having. Okay, are there any questions? No questions. Okay, there are no questions, then we move on to the next problem. So I have air at 1 atmosphere and 20 degrees Celsius to be heated at a rate of 0.04 kilogram per minute in a circular pipe of 5 centimeter inner diameter and 6 meter length, by maintaining a constant heat flux at the pipe wall. So the question now is, what is the required wall heat flux if the minimum local temperature difference between the pipe wall and the mean fluid temperature is to be equal or less than 10 degrees Celsius? Also determine the exit air temperature. So this is actually kind of a reverse problem, wherein usually you will be given heat flux and asked to find this, but when you are designing a system, so what you know that this is the temperature, maximum temperature difference that is acceptable to you. So for this temperature, you will specify what is the maximum heat flux that is possible, and then say design accordingly your insulation and stuff. So this is that kind of a problem. So we know the inner diameter. Now let's say you want to put some insulation on top of it. So what should be the thickness of insulation so that the heat flux will actually be to the whatever level that you have here. Let's say if the 10 degrees Celsius limit is there, and you determine the Q from there. Based on Q and your outdoor temperature and the surface temperature, you'll be able to determine what should be the value of insulation that you should be using so that this particular criteria is actually satisfied. That could be the next level problem that could be asked to you. These are just different variants of the same problem. So these are the values that are given to us in the question. So I'll take the values at 20 degrees Celsius, assuming that the temperature change would not be too much. Assuming that it would not be too much, I'm assuming this because the wall temperature is not given. So we can use the relation QW prime is H times TW minus TM, and you can assume it to be fully developed. First, we'll assume it to be fully developed. And if it is fully developed, I'll calculate Nusselt number. I know the Nusselt number for fully developed flow, and this is a constant heat flux pipe, so it is around 4.36, and I can substitute that to determine the H value. Once I have the H value, how do I find QW prime? Is assume that this difference is what we are saying. TW minus TM should be less than or equal to 10, which means QW prime by H should be less than or equal to 10, and from that I will be able to calculate what is the minimum value of QW prime that I will be getting, right? And once I have the value of QW prime, I can substitute the multiply with the total area to give the net heat transfer rate, from which I can determine what is the T outlet. So if QW prime increases, then T out will actually increase. So what I'll be getting here now is, if this is the minimum temperature difference that I should have, the minimum or the maximum heat flux that I should be having is so and so, and for that heat flux, what is the maximum outlet temperature that I should be getting? This symbol should actually be changed. One second. Okay, so the maximum heat flux that you can have is around 22.32 watt per square meter, which means for that particular maximum heat flux, the maximum exit temperature is 51.36. So if you have any heat flux anything higher than this, then what would happen is the temperature difference between TW and TM will actually be higher than 10 degrees Celsius, right? So now the question is, okay, are our assumptions valid or not? So we will compute the Reynolds number, and the Reynolds number is less than 2300 for tough flow, so it is still laminar. If you compute the Case number, this is around 5.56, which is more or less okay, like which is close to 1 compared to 10. So fully developed assumption is not that off. However, the most important thing here is the exit temperature is around 51 Celsius, while the inlet temperature is 20 degrees Celsius. So temperature is actually changing from 20 to 51, and it will keep on increasing. So if you recall, when we were solving this problem also, this is how the temperature profile will look like. It will keep on increasing. So the length of the pipe should be such that the delta T that you are going to have here should be minimum. But here what happened is the wall temperature actually, the temperature at the outlet, or this particular temperature at the mean temperature at the outlet is actually changing to around 50 degrees Celsius because it is air. So what happens is because of the temperature is changing from 20 to 50 degrees Celsius, that is not actually quite small. So your property values can actually change by so much. For air, the density might not change that much, but the viscosity will actually be very sensitive to temperature. So the way in which we derive the equation by assuming all the properties to be constant may not be valid at all. So whatever results that we are getting here, this maximum heat flux that we have set 22.32 is not very accurate estimate. So there will be some plus or minus to this. Whether it will be higher or lower will depend on how your property will actually vary with temperature. So you have to whatever is so this is why I'm kind of reiterating the same thing again and again. So you solve the problem and then you cross verify whether whatever results you are getting are consistent with whatever assumptions you have taken in order to derive that particular in order to come to that particular solution. Okay. Are there any questions? If there are no questions, so we move on to the next problem. This is more of a little bit of derivation here. So consider a fully developed flow of a very viscous fluid in a circular pipe of radius r equal to r naught. Obtain an expression for Nusselt number if the boundary condition is given as T equal to Tw, which is less than Tm. Tm is the mean fluid temperature. Yeah, so in the lecture videos, we have done this for a parallel plate, for a plane fluid flow, where you have one stationary wall and the other wall is moving with a constant velocity. Now, what we are saying is we're just changing the problem a little bit. So we are saying now that, okay, you don't have, you have both the sides to be stationary and the cross section is not like a plane channel, but it is a circular pipe. So determine the Nusselt number for this case. We will have to wait a little longer for you to solve this problem. I'll wait for say 5 minutes. So maybe I'll give you the governing equation. So this is the governing equation. And let's say you non-dimensionalize this by with r star equal to r by r naught, theta as t minus tw by whatever mean inlet minus tw, and u by um as 2 into 1 minus r star square. This you already have before from the Hagen-Poisson flow. Because it is a circular pipe, you can assume this to be Hagen-Poisson flow, and this is the expression for you will be having. So all you have to do is substitute it, get the non-dimensional equation, write down the boundary conditions, solve that non-dimensional equation, get temperature profile. Once you have the temperature profile, determine the gradient of the temperature profile at the walls. That will give you the heat transfer, and once you have the heat transfer, also from the temperature profile, you also need to calculate the the mean temperature. Once you have the temperature gradient and mean temperature, you can divide one with the other. In the non-dimensional terms, you can divide the gradient with respect to theta mean, and that should give you the Nusselt number. So this is a process that we have been following from the beginning. So it's the same process here. So maybe I'll wait for 5 to 10 minutes so you can solve this problem. So the first step is to be able to non-dimensional the equation and identify what are the important non-dimensional numbers that are coming up here. Yeah, the only non-dimensional number that matters here is the Brinkman number, which is given by mu m square by rho c alpha into PMI minus TW. This is again a very special case. If you observe the equation, so we have actually neglected the advection term here. So basically, this means we are assuming that temperature variation along the x direction is also neglected and axial conduction is neglected. So this is true only when you have, so this is an isothermal wall. So only when you have a very long wall where the temperature, because in isothermal case, we know that under fully, the temperature will actually vary exponentially and eventually it will become equal to the wall temperature. So only when the exponential, only when you are very far into the fully developed condition, you can assume that this particular term, that del t del x, is actually close to zero compared to the other terms. Or in another, put in another words, you can say that the viscosity is too high, that compared to the term that is here, the viscosity term, the other term, which is just the advection term, is very less. The actual velocities are very small, but the velocity gradients are too high. So you can have very small pipes with high velocities, things like that, where the velocity gradient is significant compared to the actual velocity, or when the viscosity of the fluid is very high, so that this generation is too high compared to the advection term. Or to put intuitively, what this means is the rate at which heat is being generated because of viscosity is too high compared to the rate at which it is being convected away. So that would what actually mean this Brinkman number. So if mu is very high, then what you can say is the thermal diffusivity, the scale for thermal diffusivity is very less compared to the viscosity. So the heat will not actually be taken away by convection, and that would actually be accumulated and heat generation will be much higher. So in that particular case, the delta del X term can actually be neglected, and you have the non-dimensional equation given as this, given as follows. In order to solve this equation, now you need to get the boundary conditions. So at r star equal to 0, which is along the center line, so the boundary conditions are, it needs to be symmetric because t equal to tw is a symmetric case, and then at the wall we have r star equal to 1, which should give us theta equal to t equal to tw. So which means if you substitute t equal to tw, this term will be equal to 0 and theta will be equal to 0. So those will be my boundary conditions. So now we have the governing equation. This is our governing equation and these are the boundary conditions. So we can solve this equation now. This is the equation I'm getting. So if r equal to 0, you'll have the maximum value, and r equal to 1, it will be equal to 0. If you take the derivative of this and substitute r star equal to 0, then you should get equal to 0. And once you have it, the next step is we need to find another number. So we need to know the mean temperature, which is given by integral 0 to 1 u times theta times r dr by integral u dr. So this is expression for the mean temperature. With this profile, you can substitute here. You already know the velocity profile. So okay, I should have written u by um. So okay, let me just correct that as well. You can just proceed with that. So I'll just write this as okay. This I'll put u star, and this I'll write it as u. That should solve the problem. Okay, I'll just make the correction so you can solve this in the meantime. I think it is consistent. So this u is basically 2 into 1 minus r star square, which you can substitute here to get the theta m. Yeah, of course, theta m will be a function of Ringman number. So were you able to calculate it? I'm getting this around 5 by 6 here. So maybe one of you, if someone actually solved, you can confirm if you're also getting the same value. Okay, now I have theta m. So how do I calculate Nusselt number? Use the relation as minus theta. This is the non-dimensional value, so this will be the equation. If it is not, if you are considering in the dimensional terms, then it will be minus k times del t del r at r equal to r naught divided by, yeah, tw minus tm, right? So but here we do not need all of that, so you can directly compute this. So you already have theta, so you can substitute that here and get nu if the number is r naught, but usually we express in terms of hydraulic diameter, which is 2 times r naught. So NUD is basically 2 times NU r naught. Whatever expression you are getting here, multiply that with 2, and that you should be able to solve this. If I substitute the values, I'm getting this around 9.6. BR actually cancels, like the derivative here has a BR term and this has a BR, so both will cancel, and you will be left with a constant term. So that will be around 4.8. So if you multiply with 2, I'm getting around 9.6. So yeah, you can quickly do the calculation and let me know if you're also getting the same value. Yeah, okay. So this is the last problem I have for this week. So consider the fully developed flow for a viscous fluid between two parallel isothermal plates separated by distance of 2d. So in the previous problem, we have considered the symmetric case where all the entire wall is at a constant temperature, axisymmetric case. Now let's say you have two parallel plates and both of them are maintained at different temperatures, TH and TC. Let's say the top one is TH and bottom one is TC, and the plate separation is given by 2d. So this is a parallel plate flow, and assume it to be fully developed. So what would be the Nusselt number for both the plates, and what would happen if okay, this is a viscous fluid flow because of heat generation. So here the important questions would be what would be the heat flux, obviously what would be the Nusselt number on the top and bottom plates. That's the natural question to ask. And then let's take the limiting case when TH equal to TC, then that should be equivalent to whatever the isothermal, like the symmetric case that you would have, so you would eventually go there. And then the next important question is what would happen to the maximum temperature of the fluid. Now we are saying that the top and bottom plates are maintained at fixed temperatures. So if the viscous heating is usually, if it is very less, then what would happen is both top and bottom plates will actually be maintained at their temperature, so there won't be any problem. But if there is actually very high viscous force, then what would happen is viscous generation or the internal heat generation will be way higher, and these plates would not be sufficient to actually take up all that heat. Then what would happen is the bulk temperature of the fluid will actually be higher than both of these temperatures, TH and TC. That could also happen if the internal heat generation is higher, so that you are not able to take away or dissipate the heat in any way, then that could also happen. So in this question, you are asked to derive the relation first for Nusselt number and then identify the limiting case for TH equal to TC, and then if possible, maybe you can also plot the temperature variation as a function of y and see how it varies for different heat generation rates. So the governing equation is given for you here. And for fully developed flow, we know U is given by this expression, which we already derived like a couple of weeks back, I guess. We can substitute that in the again, as I said before, because we are assuming that it will be very viscous fluid, we are neglecting the convective advection term. We have the diffusion and viscous energy. So whatever is internal heat generation because of viscous forces are taken away purely because of diffusion and not because of advection. So that is the assumption that we are considering here. Of course, you need the boundary conditions also. Let's say the bottom wall is TC and top wall is TH. This is some arbitrary thing. You can just do the reverse as well. It doesn't matter. Basically, all you are doing is you're just changing your coordinate system accordingly. First, you non-dimensionalized equations with this non-dimensional numbers. So why are we doing this is just to understand what are the governing parameters. Now we have too many parameters and we can't vary all of them. So let us see how many non-dimensional numbers we get. So if you do the non-dimensionalization, so I have only one parameter here, that is the Bigman number that needs to be verified. So unlike the previous problem here, this is a constant source term. So this is very straightforward to solve. You have the boundary conditions at y equal to -1, t equal to tc, so this will be equal to 0, and at y equal to 1, you have t equal to th, so this theta will be equal to 1. So these are the boundary conditions, and this is a governing equation. Yeah, so you can quickly solve and find the expression for theta. Yeah, you have to first find C1 and C2 by substituting these boundary conditions. Okay, I hope you have solved it. This is expression for theta. And once you have theta, to determine Nusselt number, you need to calculate the mean temperature and then take the derivative at the corresponding values, divide it with the mean temperature, and then that will give you the Nusselt number. It's straightforward again. So I'm getting mean temperature to be like this and have done the Nusselt number calculation. Just note this sign changes here. Why I have taken this is because the heat transfer here would be reversed. It will be against in the reverse direction at the bottom wall compared to the top wall. This was not the problem in case of the circular pipe because it is always radially outwards, so we don't have to worry about it. But now here we have a different direction because the denominator will consider wall minus this. So yeah, that should actually be the case. Yeah, so you should probably be considering that way. So one would be theta m minus, for example, if you are considering on the top wall, should be theta minus 1, or basically because for the hot wall, theta is 1. So this will be theta m minus 1. The assumption is, and for the other side, it should be theta m minus 0. So one will be theta m and another one will be theta m minus 1. Yeah, that. Yeah, so you can quickly compute those values and let me know. So I'll make the correction accordingly. To those of you who are familiar with MATLAB, so yeah, these problems, instead of actually solving them with hand, you can also use something called symbolic, where these the MATLAB will actually treat these as not as numbers, but then as the variables, like as you would do normally. So you can directly input the equations like here. So in this case, we have u equal to 3 by 2 times 1 minus y square that I have given here. And the differential equation you can directly give as differentiation of theta with respect to y, which is a second order derivative, plus dr times whatever del u del y whole square. So it will give me the equation that I have already written, that del square theta del y square plus 9 times dr y square equal to 0. So with this equation, I think there is a typo here. There is a y square term that is coming here. I'll make the corrections when I upload it back. So with this particular equation, you can directly use the dsolve. Dsolve is a function that will directly solve the differential equation, and you can give the boundary conditions. So at theta equal at y equal to -1, you have theta equal to 0, and at y equal to 1, you have theta equal to 1. So if you give this in this particular form, it will actually solve for theta and give you the solution. So this is a solution for theta I'm getting. So once I have the theta solution, I can calculate theta mean. Theta mean is basically integral theta times whatever solution I have times velocity for y within the interval -1 to 1 and integral u times y -1 to 1. So that will give you the theta mean value here. And then the Nusselt number are calculated by, you take the differentiation of theta with respect to y. So theta with respect to y, and then substitute 1 in place of for the top one and -1 in place of the bottom one. And here you have pointed out, so this should be theta mean -1, or it is basically from the wall to this. So I've already taken care of that. If you are not taking the minus here, so on the top wall, so the net heat transfer from the wall to the fluid. So we or we'll consider one way. So if it is minus here, so this will be the net heat transfer from the fluid to the wall. So this will be HW theta mean -1. Similarly, if you do it on the other side, so from the fluid to the wall, so this will be minus this divided by theta mean is the fluid temperature -0. If I compute the values, so these are the values I am getting accordingly. For the hot wall, so that is around 3 Br minus half by this. And for the cold wall, I have the other value. So let's ignore this for time being. Now, the next question is what would happen in the limiting case where the Brinkman number will actually be tending infinite, or when TH equal to TC, this BR will actually tend to infinite. So what would happen is you just substitute that, and then I'm getting this value around 35 by 8, which is around close to 4 point something, which is the case that you would get when you have an isothermal wall. So this would actually tend to an isothermal wall eventually when the Brinkman number is very high. Or the other scenario where you have the BR actually tending to 0. When BR actually tends to 0, you can see that substitute BR equal to 0 and you get hot wall to be 1 and the cold wall to be -1, which is also consistent with whatever we have been discussing. Like what would happen if BR is 0 is basically your fluid is not actually moving. Then all you are having there is pure conduction. When you have pure conduction, Nusselt number should be 1. And for the hot wall, it is positive, and for the cold wall, it is negative. If you want to account for the sign directly in, like for it, then you can just remove the minus there, and then you will get accordingly. Like both of this to be 1, and then you get these values. So I'll make these corrections in the slide and then upload them again. And you can find all of these slides in hosted on my GitHub page, which is given as follows. So I'll just post it in the chat box. So you can go there and then you can visit to this particular week. So in between weeks, I have not uploaded yet. You can visit from week 7, and then you will find all the slides along with questions and answers to them. I'll update this once the session is over. You can find it here. I'll also upload this in the Google Drive folder that is shared with you from the NPTEL. Okay. So these answers are a little off now. I'll just update them. But this is around close to what we call 4.375, which is higher than this. But when you compare this value with the constant heat flux case, so when you have a constant heat flux wall, then this value is close to 4.36. So this is also 4.375. These values are close together, close to each other. Okay. Are there any questions? Right. Yeah, I guess there are no questions. Thank you for joining. And next week, we'll be starting the natural convection. We'll meet at the same time, Saturday 5 to 7, and we will actually solve problems. So please go through the lecture videos before attending the problem solving session. So if you have any queries, you can raise them during the session. We can discuss them. If you do not have any queries, then maybe I'll take up some problems, and then we can you can solve those during the session. And while solving, if you have any queries, we can discuss them. Yeah. Yeah, then we'll call it a day. Thank you for joining. We'll meet next week again.